Hello, everyone. Welcome to our crash course on optimizing big memory workloads. I'm the MC for the presentation, but you'll be hearing from Gerald Kunzman at phoenixNAP, Glenn Otero at TGen, Charlie Yu at MemVerge, and my colleague Sridhar Kayathi at Intel. So these are the 4 courses that are in our crash course. The first lesson is about infrastructure challenges for AI ML processing, and that's what Gerald will be covering. The second lesson is brought to you by my colleague Sridhar, which is how to optimize this kind of special memory product called Intel Optane Persistent Memory. And the third lesson is from MemVerge. Charlie Yu is presenting that, and the last one is Glenn Otero at TGen, who's showing you actually a practical application of all of this technology used together with single-cell sequencing. And then we'll end with some Q&A. So we have a giveaway that's going to be happening. We have a $100 Amazon gift card, which we'll talk about at the end of the presentation. So there's some poll questions here. We're going to run the poll, and we'll give you a chance to provide answers. Hopefully we'll get your input here about whether you use big data analytics or not. Okay, and now we have the results. So well, that's a perfect 3-way split. So we have a third of the people who are fully adopted, a third who haven't started, and a third are in the middle. Very interesting. I'm not sure how many votes we had, but that those are interesting results. After this, we have a second poll. Okay, well, this is quite interesting. So we see that most people, I guess, have all of the above, but there are some people with data security issues or concerns, and some complexity issues from an infrastructure side and scalability limitations. But it's really encouraging to see that everyone is still trying to figure this out. So perhaps they'll learn something here. Okay, so with that, what I want to do is just hand the presentation off to Gerald, and he'll take it from here. And I'll be back with you after this lesson.
Perfect. Thank you, Michael, so much. So my name is Gerald Kunzman, and I'm the Intel ambassador at phoenixNAP. Today, I wanted to talk to you about some of the challenges encountered with infrastructure for AI and machine learning processing. So on the next slide, let's start with taking a look at some of the trends we're seeing with data. So many of the activities that drive our day-to-day is fueled by data, right? When we look at the global data sphere, we can see massive acceleration in the growth of data generated. The global data sphere is expected to grow to more than 180 zettabytes by 2025. And real-time analytics makes up approximately 30% of that data. So organizations are continually looking to get results, augment their workflows, and make decisions in ways that are faster, more precise, and more efficient, and are more and more frequently looking for ways to extract insights from data, and are exploring and driving innovation in artificial intelligence. So the global AI software market is expected to reach about $126 billion by 2025, with finance, healthcare, telco, retail, and the technology sectors really leading the charge in that space. So let's take a look at some other trends that we're seeing on the next slide. So another trend we're seeing is organizations really are struggling to keep up with the data they produce. Organizations are really they're generating more data than they've ever generated before, but are struggling to find ways to make sense of that data, right? And to find meaningful ways to actually utilize and act on it. So in a survey, 38% of the respondents agreed that the complexity and just sheer volume of data that was produced made it very difficult to generate any kind of real business value from it. Another survey showed that 97.2% of the organizations surveyed by Conductor say they're now investing in artificial intelligence and big data. And IDC predicts that global data creation and replication we'll see a compound annual growth rate of 23% through 2025. So looking at these trends, they indicate data growth isn't slowing down anytime soon. And organizations will continue to really need to invest in the tools that help them interpret and make sense of the data in ways that actually deliver, meaningful insights and value to the organization. So looking at some of the challenges, right, with processing AI and machine learning workloads, these workloads, they tend to demand a lot of compute horsepower and resources that really might exceed the infrastructure capabilities that might be available on-prem within the organization. Additionally, AI and HPC deployments can require a lot of power. According to Forrester, power demands increase an additional 30 to 50 kW per rack. And that kind of power density requires a lot of specialized data center space, equipment, and expertise to actually build it and manage it. Collecting and processing data is another challenge, right? So especially when we're looking to ingest it from geographically distributed sources, this can add significant complexity in implementation and monitoring. And then of course, security. As we look at security, that's always a concern and a challenge, especially when working with sensitive data such as financial details or PHI or some other kind of sensitive information, right? And then as we progress, getting into scale, that presents a very large challenge for most organizations. AI and machine learning at scale needs a lot of flexibility around capacity, performance, data retention sources, as well as the ability to rapidly adjust and actually optimize infrastructure to any kind of changing needs that might be occurring within the organization, while all at the same time simultaneously, maintaining availability and security. And many of the components of AI and machine learning infrastructure deployments requires, diverse skill sets across the organization, right, to be able to actually properly manage and execute implementation. And for a lot of organizations, this can be a really big challenge, especially trying to deliver all these expertise on-prem or internally within the organization. So at phoenixNAP, we really specialize in building and supporting complex infrastructure solutions. And we also work with great partners like Intel and MemVerge and TGen to make sure we're providing technologies that can help organizations augment their resources and tackle a lot of these challenges by gaining access to elastic and highly scalable data center resources, compute, security, as well as experienced staff, and as well as access to powerful software and hardware technologies. So on the next slide, let's take a look at some of the hardware limitations for processing big data, right? So when dealing with big data, there can be a number of hardware limitations. To start with, price typically is always a factor. We can always throw additional hardware resources at a problem, and that can certainly be an option, but a lot of times that might not be the most cost-efficient option, right? Many times there's going to be better options for leveraging software or specialized hardware components that can significantly help a workload and more efficiently utilize the underlying hardware, right? The underlying hardware resources that are available. You also get into budgets where maybe purchasing hardware on a CapEx model can also pose a challenge for an organization, especially when we're building on-prem. So it might be worthwhile looking into ways to accelerate delivery, right? By leveraging an OpEx model with a cloud provider that can actually deliver the capabilities that are needed for the project. So with big data, it tends to also demand a lot of capacity around storage, compute, and network, and that can pose challenges, right, when you're trying to build on-prem. When we're dealing with processing data in memory, bringing data in memory will bring it closer to the CPU, which of course is going to help boost performance. But at the same time, right, we know DRAM can be very costly, and we also might run into limitations on the hardware's capabilities, right, in terms of capacity. And then on the piece of on accelerators, right, lack of access to accelerators for AI and machine learning workloads can also impact performance. So simply getting raw compute resources isn't always enough, right? We might need access to some of the underlying accelerators, and not having that access may require us to do some tedious tuning and other workarounds. By utilizing scalable infrastructure solutions that give all the right tools, including access to these accelerators, we're able to achieve superior performance and really accelerate deployments, and overall just deliver significant savings in terms of costs and time. On the next slide, let's take a look at some of the features and accelerators that are available with the third generation Xeon scalable processors. So the third generation Xeon scalable processors provide several different features, right, that we can use to help accelerate workloads. Intel Deep Learning Boost delivers embedded performance and flexibility that really can allow you to run complex AI workloads on the same hardware that might actually be running your existing workloads. And then Deep Learning Boost extends the Intel AVX 512 instruction set with Intel Inference Boost to provide significant performance increases for deep learning workloads, such as image classification or speech recognition, object detection, amongst several others. When we look at working with confidential data in various scenarios, right, that can be challenging. So with Intel Software Guard extensions or Intel SGX, we actually have the ability to partition apps into CPU hardened enclaves. And this can open up a number of possibilities in the confidential computing arena, right? Such as we can securely conduct machine learning across broader data sources while maintaining or ensuring our algorithms and data sets remain confidential. So that gives us a lot of different paths that we can take when working with confidential data. And then with Intel Optane technology, Optane technology really redefines how we think about memory and the storage hierarchy. And it allows us to bring very large data sets closer to the CPU that might not be possible or might be cost prohibitive to do with something like DRAM by itself. So with Optane, Optane is going to deliver DRAM-like performance without all the cost or capacity limitations that DRAM comes with when using it by itself, while also maintaining a data persistence while in memory. So with that, Michael, I'll hand it back over to you so we can dive deeper into Optane Persistent Memory.
Right. Thank you, Gerald. Our next speaker is my colleague from Intel, Sridhar, and he will go into detail about the Optane Persistent Memory product. Take it away, Sridhar.
Thanks, Michael. I think as you heard, the digital transformation has been happening across the industries, especially in big data, machine learning, AI, and all those things. And we are seeing few trends, right? One is in the digital transformation is definitely fueling the demand for the compute. And because the demand is going up on the compute needs more memory to process more data, right? So that's where the demand for the memory is also going up. That's one trend we have been seeing. And also because of the data explosion we are seeing in the industry, as Gerald has shared before, the data has been growing at 23% year on year. So the memory needs are also going, and we are seeing that the DRAM is not keeping up. As you can see in the middle, from last, I would say 20 to 30 years, the DRAM has been growing, but in last 10 plus years, the density of the DRAM growth has been not meeting up the expectation. Whereas on the CPU side, if you see, or on the compute side, if you see, the cores are going up drastically. But whereas the memory density and the performance needs are not meeting that needs, right? That is one problem. And also we are seeing that across the industry, before it used to be in few hundred gigs or even less than 100 gig, but now the trends are more moving towards terabyte or more memory. And that's where this technology called Optane Memory is going to help, and I'm going to talk about more. As you can see here, what Intel has done is, in more than a decade back, we have been working internally on this technology called Optane. Optane is a you can think of like a brand name for a 3D crosspoint material that we have created, which is a transistorless but not a NAND technology. It's a byte addressable and it gives a very low latencies. And that's where what we have done is we have taken that technology and made it into two technologies. One as a persistent memory, which will look and go into the DRAM slots and which will give in nanosecond latencies, and other technologies like NVMe SSD that is for more solving to accelerate the storage performance needs. And as you can see here, what we are doing is, as I stated before, DRAM is not scaling the way we want. It's still in 32 to 64 gig is more the sweet spot for per DIMM capacity in DRAM. Whereas with Intel Optane Persistent Memory, we try to solve from the capacity side, and also our latencies are still in nanoseconds. We give something like 300 to 400 nanoseconds. And also, we not only give the capacity and very low latency, we also give persistence. That's where we are going to talk more about how MemVerge and TGen was able to take advantage of that persistent characteristics with this technology that previously was not able to be achieved with a DRAM solution, which was a volatile technology. As you can see here, this looks and feels like a DDR4, just the technology we have used is different to achieve these larger capacities. We come anywhere from 128 GB, 256 GB to 512 GB. Because of these large capacities, we are able to get up to 12 terabytes memory on a two-socket system, which was not thinkable before with the DRAM technology. And also, it gives performance very close to the DRAM because of its nanosecond latency. And also from a cost perspective, if you compare a 128 gig PMem technology or Intel Optane Persistent Memory DIMM to a 32 gig DRAM, they are almost on par on the pricing. So it's almost like you can reduce more than 50% cost on your system, or you can almost double the memory for the same cost. And also, we give is highly reliable. We have all the RAS ECC capabilities. And also, we have additional security capabilities that are not there in the traditional DRAM, which is hardware encryption. We have hardware encryption for customers who are looking for securing their data even at memory. And we also can take advantage of persistent characteristics. That's where MemVerge is going to talk about how they can take advantage of that persistent characteristics and how TGen has seen the advantage. And also it could be, because it has persistent characteristics, it could be even used to accelerate some of your storage needs, like for metadata or caching also. We have been working on this technology for more than a decade, but we have launched this technology, made it available through all your favorite OEMs. In last 3+ years, we have launched in 2019 beginning, and we launched with the 100 series or first generation PMem, which is compatible with our second generation Xeon scalable processor, or codename Cascade Lake. And we were able to achieve up to 4.5 terabyte per socket. And we were having a speeds of 2666 mega transfers. And at that time, we had 6 channels. And then last year, we have launched our 200 series, or our second generation PMem, which is compatible with our third generation Xeon scalable processor. In that, we have increased the number of channels from 6 to 8. And also from gen to gen, we have increased the cores and performance, and also the speeds. If you see, we have went from 2666 to 3200 mega transfers. And also because we have increased the number of channels, we are now able to get up to 6 terabyte memory per socket. That's why we were able to get down to 12 terabytes on a 2-socket system. Apart from that, as you can see, we are helping you to process larger data sets and give you the persistent characteristics, and also solve the cost problem. Because of recent supply chain issues, we are seeing the cost of memory has gone up drastically in last 1.5 years, and that's where PMem is going to help you to lower your cost. And also we use AES 256 encryption at hardware level, so that your data is encrypted on rest. And just want to show you the roadmap also, right? As I have talked before, we have already launched our first generation and second generation PMem. They are compatible with their respective generation Xeon scalable processor. They are not interoperable, so that you can see second generation will not run on a second generation Xeon. It needs a third generation Xeon. I'll talk a little bit more in the follow-up slide why that is the case, but they are not like interoperable. So there is a dependency for each generation of PMem to the specific generation of Xeon scalable. And the third generation is coming out in the second half of this year with the fourth generation Xeon scalable processor, or codename Sapphire Rapids. And then we are from a fourth generation PMem, when we go there, we are moving from a DDR4 and DDR5. When we are coming out with third generation, we'll be on DDR5. But when we go to the fourth generation, we are changing from a DIMM form factor to more CXL. That way, it's an open standard, and it has been adopted widely by the industry. And that's where in our future generation with our Granite Rapids, that's when this technology is going to be available in next couple of years. And I want to spend a few minutes here. So as we talked before, this technology is great. It helps you in larger capacities. It has persistence. It is lower cost, but also it gives you some flexibility also when how you want to use this technology. We call it modes of operation, how you want to consume this memory. There are basically two modes. One is memory mode. Another is app direct or application direct mode. Today's main focus will be on app direct, but maybe I'll spend few seconds on memory mode also. Memory mode is mainly targeted for customers who are just looking for large memory. They don't have applications which are modified, or they don't need anything except a large memory as a volatile. Then they could do this at BIOS level. All the OEMs have this BIOS now where you can go to BIOS and just change the mode to memory mode or app direct mode. In the memory mode, as I stated, this is completely done at the Xeon level, memory controller level. So where you still need some amount of DRAM, but Optane memory will act as your main memory, and DRAM will become as your L4 cache. Now let's talk a little bit more about app direct. This is where application need to be modified, where we have worked with ISVs like SAP HANA, like Aerospike, like MemVerge, which even has some additional advantages beyond like specific ISVs, because with MemVerge type of technology, it can act as a middle layer where it can provide all the app direct benefits to the applications, not changing the application. So you can think of like almost it's giving a memory mode type of features on app direct without application modification. And this is where Glenn is going to talk, and Charlie from MemVerge is going to explain how MemVerge technology is going to take advantage of this app direct, and how their snapshot capability and persistent characteristics are going to help customers in fast recovery times also, because the data sets are growing larger. I'll hand it back to Michael. Thank you.
Yeah, thank you, Sridhar. So our next presenter is Charlie Yu from MemVerge, and he's going to talk about their memory virtualization products. Go take it away, Charlie.
Great. Thank you, Michael. Yeah, hi. So let me dive into details on how we do that. So Sridhar talk about the great hardware Intel built for the memory market, the Optane Persistent Memory. And as you know, in order to get the most out of your hardware, you want to have that paired with a great software, and that's what MemVerge comes in. So we are a software company, and then we build software that is purposely designed around memory, and not just Optane memory, but all types of memory. And once you have the software, now over time, every couple of months, you can upgrade the software in order to get the latest innovation from the software technologies. So as your hardware gets installed over the years, every iteration of the software upgrade give you more and more feature and then capabilities that can maximize the investment you have in the memory. All right, so from our architecture standpoint, you may wonder, well, what does it take to use this technology in my machine? Do I have to install some kind of a kernel module in order to take advantage of this? The answer is no. Our software actually works in the user space. So it works any flavors, stock Linux kernel. So you can use all these versions that's available out there, and you simply install our software in the user space, and then you can take advantage of the features I'm about to talk about. One of the first things we do is around memory tiering, right? So in your system, you may have DRAM and a PMem, and you may also have NVMe SSDs, right? You have different types of media in that particular machine. And what we do is we take all these media into consideration, and then we can actually create a memory virtualization across all these type of media. And that will essentially give you a much greater addressable space for the memory applications. And not only that, we also have a mechanism allow us to tier the data between all these memory technologies intelligently, right? Because it won't be very useful if the data always hitting the slower tier of the memory, and that will lead to less performance in your application. So ideally, we always want to make sure that most actively used data, the hot data, are always sitting at the highest memory tier, and then we want to have the slower data sitting on the slower tier, right? For example, SSDs. So that's what our software does. In the memory tiering service, it does exactly that. And not only this, we're also supporting other new memory technologies that is not even available on the market yet, such as the CXL technology that you will hear in the industry in the next 6 months to the next few years. That's emergent memory technology that is going to add much greater capacity to the market. The second feature we have in our software stack is called in-memory snapshot service. So you might be familiar with Snapshot on storage on disk. It's been around for 20+ years. And what we essentially doing here is to add a layer of technology that can capture that in the memory. And I'll talk about in more details in the next slide and how it works. Okay, so the name, we call it zero IO in-memory snapshot. Zero IO means there is no IO created when you snapshot something, right? All happens in the memory tier without introduce any serialization, deserialization. Is all happened in the memory tier. So our snapshot at the core, what it does is basically it captures the metadata of all the memory pages. So there is no data movement, right? All happens in the memory layer, especially if your data is already sitting on the Optane Persistent Memory, because that media in itself, it is already persistent. You can lose the power, come back, the data will still be there. And our snapshot basically captures all your data in the CPU registry, in the cache, and then we will store that in the Optane PMem. And that capture is the snapshot, is the memory snapshot. So we'll do that. And the overhead also is very minimal. We're talking about in the neighborhood of just number of megabyte range, right? So it's a very light overhead, but give you such a capability that make things much faster. So the basic snapshot uses this mechanism. And another technology we built on top of this is called ThinClone. ThinClone basically making copies of this metadata, so we can essentially create multiple copies of the same application on that particular system. And then we do all that without require extra memory for this. And then we'll talk about more use case on how customer can take advantage of this kind of capabilities. The third term we will introduce here is called App Capsule. So we have the memory snapshot, right? We have all these metadata we captured. And the next thing is we want to combine that with the data sitting on your storage, because the application itself is not just about the data in the memory, also about all the files, all the data sitting on the different storage types. And App Capsule captures all of that, and then it can move the application locally or remotely into the cloud, things like that. So that cloud mobility comes from App Capsule. Okay. Now let's talk about some of the best practice. Right? How do you use the technology, and how do people typically take advantage of this kind of snapshot capabilities? The first thing is how do you snapshot something, right? It's actually very simple. It's one command allow you to take a snapshot of your running system. And anything that is in flight, it's running in real time. it's basically frozen for milliseconds, and then the snapshot is taken, which capture the running state of these applications. You can do that manually, or you can schedule that, let's say, every 5 minutes. So in about 10-15 minutes, you can have 2-3 snapshots created, and that's how you snapshot something on that particular machine. It's very easy to do. So what are the benefits, right? I've done the snapshot, so what are the benefits we bring to the application? Well, first of all, it's in the area about loading and saving and recovery, right? When your memory footprint is in the neighborhood of hundreds of gig or maybe in the terabyte range, to load that data from storage into memory or save the data back from memory to storage is going to take some time. It may take 20 minutes, half an hour or so. And having in-memory snapshot allow you to switch between the different states in less than a second, right? So it's very quick to load, save, and then recover from your memory snapshot. So you can essentially move data, terabyte of the data in fraction of a second. The other best practice, the other benefit with this snapshot is recover from a long-running job, like a pipeline. Some of the applications that we're seeing out there, they're not native built with a lot of fault tolerance. So if you have a long-running workload, long-running job that takes days, maybe weeks to run, when that particular application crashes in the middle of it, the recover might be going back from several days ago or several weeks ago, and that's not really desirable. So with the snapshot, with a memory snapshot, if something happens, right? If you lose the power in the data center, if the application runs out of the memory, it crashes, we can easily recover that in fraction of a second, and it can get you back from maybe 5 minutes ago, right? So for you to recover from that point, it's much easier, much faster to do. Okay. So now let's move on to talk about the other benefit, the thin clone, right? So thin clone basically makes copy of the snapshot, and we can share that snapshot across multiple applications. And thin clone is a way to essentially create multiple copies of the same application on the same machine without using any extra memory. So that's sort of the building block on how the technology works. In the same way, in a very similar way, you know, if you have used storage clones in a very similar way, right? You can do that without using extra storage on your system. So we basically do something very similar in the memory layer to allow these kind of capabilities. The benefit for thin clone is actually very powerful. Let's say if you're running a pipeline, right? You're running multiple stages of workload, and then typically in order for you to derive some results, you have to run through that pipeline from A to Z, generate some results, and then look at the data and say, hey, you know, what if I've changed some parameters in my computation, and then what would the result look like? You make that change in your computation, and then you rerun it, and then hours later or maybe days later, you get another set of results. You do the third time to get the third set of results. That obviously is very time consuming, and it's very sequential, right? So with memory thin cloning, you can essentially snapshot at the very beginning, right? Once you reach the first layer of the results, you can say, hey, let me snapshot this, and I will generate 3 copies of that snapshot. And with the 3 copies, I can essentially run all 3 at the same time, right? And that will give you 3 results at the end of the run. So you can dramatically increase the efficiency and then arrive the results much faster with this type of capabilities. And then finally, App Capsule. So App Capsule, as I mentioned earlier, is basically the encapsulation of the memory snapshot as well as the data sitting on your file system, right? So it's encompass everything to move that application from local machine to local machine or to a remote machine. And the benefits comes from several. One is mobility on the local network, right? So you may have an application, it starts out using X amount of memory, maybe less than 100 gigs of memory, but over time you realize, hey, it's growing, expanding, it's allocating a lot more memory to a point that it may run out of memory, right? So what do we do? Without MemVerge, you may have to shut it down. Hopefully, can saving the state, and then copy that over to another machine, and then reload the data from storage into memory, and just kind of like restart it from there. With our memory snapshotting and the replication feature, you can actually snapshot something in place in that machine with a small amount of memory, and you can replicate that memory snapshot to a remote machine and resume that workload from the second machine, which should have much greater memory. So your workload is not lost, right? You don't have to start from the very beginning. So memory, so App Capsule is what allows us to do that. Also, in some cases, you may want to take advantage of the cloud, right? The phoenixNAP bare metal cloud. You may say, hey, I have, let's say 10 machines over here. I'm running this type of computation, and at a certain point, I've realized that I'm running out of capacity. I need more computation to run my workload. Let me burst that into the bare metal cloud to sort of borrow additional computation for my running workload, and I'll return it once that that job is complete. And you can do that again using the memory snapshot, bursting, come back when you're done with this. And again, that's all enabled by the memory capsule. Okay, so yeah, I touched upon some of the capabilities we have with our software. So now I'm gonna hand over to Glenn, and he will describe some of the actual real-world practical usage of this technology.
Thanks, Charlie. My name is Glenn Otero, and I'm the VP of Scientific Computing at TGen. And my role here is to essentially accelerate, optimize the performance of all our genomic sequencing analysis pipelines. So TGen is based in Phoenix, Arizona, and we're a nonprofit research organization working in the areas of precision medicine and translational medicine, focused primarily on cancer, neurological disorders, diabetes, and rare childhood disorders as well. And we've been using genomic analyses and sequencing to address all of those research areas. And TGen was founded in 2002 by Dr. Jeffrey Trent, who was the founding scientific director for the National Human Genome Research Institute. So the work I'm going to describe today was first published in 2020 in Science Advances, and is still ongoing. And so this is one of the reasons why we chose the application here for IPF to accelerate and to better perform on our HPC cluster. So IPF, or idiopathic pulmonary fibrosis, it's a relatively new progressive disorder, clearly doesn't have any known cause, and the prognosis is pretty grim. Without a lung transplant, within 3 to 5 years, death is the result. And current treatments, essentially only ameliorate the symptoms, and any known treatments also provide major side effects, unfortunately. So for those not really familiar with single-cell mRNA sequencing, the slide is obviously a gross oversimplification, but essentially for this study, samples of tissue from IPF patients were taken, and samples from 10 control lung patients were taken. The cells are dissociated from the tissue, and then those cells are sequenced. And the goal is to essentially look at the gene expression in each individual cell and try to group those cells into populations based on markers that they express, so that we can then kind of compare and contrast the patients versus the controls to see what's changing and what could possibly be causing at a cellular level IPF. And so what the initial results found were that there is this KRT5 plus, KRT 17 plus population that was it doesn't match any of the other biomarker profiles that was thought to be important in the development of IPF. So the analysis took a long time though. So in order to get those populations of cells kind of sorted out and graphed out in that manner, so you could actually see the different populations, the analysis looked at 114,000 cells and about 30,000 genes each. And so it's a relatively large data set at the time, several years ago. I mean, now single cell data sets are above 1 million cells sometimes, but back then this was the largest experiment that TGen was doing from a single cell perspective, and it was taking several hours to complete. It was written in R. Several parts of it were written serially, and we saw kind of on our horizon that single cell sequencing is only going to continue to get more complicated and burdensome because of the cell counts that we were starting to analyze in experiments, and also the type of software that our researchers were writing wasn't particularly efficient with regard to memory usage or parallelization. So this pretty eye chart kind of shows the before and after the analysis, before we applied using MemVerge technology on the left, and then afterwards on the right. So walking you through this, on the left-hand side, you can see the process of analysis is just very serial from end to end, right? And the color-coded steps in there can be associated into their own essential pathways. So in running this application serially, it was taking over 6 hours to run, and after that, researchers wanted to tweak parameters and rerun it and rerun it and rerun it and just iterate with parameters and rerunning the analyses. So they've often found themselves logged into RStudio for a really long time and just trying to do these iterations. So what MemVerge allowed us to do was a couple things, and one is that we could take a snapshot at a point in the analysis where there was basically a common ground, and we could split into the 4 different color-coded pathways. So instead of running them serially, we could use the cloning capability to take a snapshot and then replicate it multiple times and run those 4 pathways of analysis essentially in parallel instead of in serial. And so that saved a lot of time, about an hour and a half time there. And then when we wrote out the results of the analysis, instead of essentially writing to disk and after the big merge, we could actually just keep it in memory, right, and take a snapshot of that. So overall, this saved us a good chunk of time. And the working with MemVerge also, their engineers wrote the code that we could stick into our R program that would essentially automate this, so we didn't have to sit at the command line and wait for things to get done and do the cloning and the snapshotting manually. So that was a really big help for us. So as you can see here, we had a 36% increase in running that particular workflow. There are going to be more IPF experiments in the future, and we know those data sizes are going to be larger. So we actually expect to keep improving upon this and actually leveraging App Capsule and some other technologies that Charlie mentioned to actually start moving these applications around the cluster. So if they were going to run out of resources on a particular node, move them to another node or to somewhere in PNAP's cloud. I'll briefly mention in a different application that wasn't single cell sequencing, but it was still RNA-seq and splicing related. We had an application that was taking over 2 months to run because it was building this really huge graph structure, but it was always crashing. And then the researchers were having to start over and over and over. And it was very, very frustrating, obviously. So MemVerge also helped us by taking a snapshot after every time we added a node and edge to the graph, and it prevented any crashes, right? Or if it crashed, we could just recover right from the last sample that was added. So, and allowing us to do that actually, and some more optimizations, we were actually able to make that application run in just 13 days compared to 60 days. So we plan on working with MemVerge a lot more in the future as a lot more of our applications start becoming really memory intensive. Michael, I'll pass it off to you.
Thank you, Glenn. I think that the final few slides, I think Gerald might be covering for
Thank you,
these. I'll let him take it away.
Perfect. Thanks, Michael. So yeah, thanks everyone. At phoenixNAP, right, we have a lot of different services available in our product portfolio that we can provide to help solve some very complex challenges, right, around different types of workloads and the infrastructure needs that they may require. So within our services portfolio, we have a number of different solutions for infrastructure, including our data security cloud, which is really a product that for folks that are focused on various security services, right? If you need compliance for PCI or different security levels for enhanced encryption, and something that's built on a VMware stack, we're able to deliver that as a service where you can deploy the resource pools needed within Data Security Cloud. And then we have a number of different services available for hardware infrastructure, including our dedicated server offerings where you can deploy on demand different bare metal types that you might need for workload specific infrastructure, as well as our bare metal cloud, which is our API driven cloud infrastructure for bare metal, where you can actually deploy through either API or your favorite infrastructure as code tools over 40 different instances of true bare metal infrastructure on demand. So you're actually able to deploy those instances in just a matter of a couple minutes for various types of workloads. All of our services are powered by Xeon. In bare metal cloud, we also expose a lot of different feature sets for accessing instances with Intel Optane Persistent Memory, as well as other features like SGX and software guard extensions, excuse me. And if you need a custom solution or something that's single tenants and built to spec for a very specific workload, we also have the ability to do hardware as a service where we can deliver customized and fully tailored hardware solutions in a single tenant colo environment and still deliver that same kind of flexibility around OpEx for scaling up your infrastructure. So with our bare metal cloud platform, we have locations available in the United States, Europe, and Asia. We have the latest generation Xeon scalable processors as well, including Intel Optane Persistent Memory, where we can actually deploy a bare metal cloud instance type with Optane Persistent Memory, as well as the MemVerge Memory Machine software. And all of our bare metal cloud instances have access to S3 compatible object storage that you can provision for your different instance types, as well as onboard NVMe flash storage. And each node has the ability to have up to 50 gigabits of transfer speed, whether that's for public or private networks. So you have the throughput capacity that you might require for a big data project or any kind of AI or ML workload you might be running. In addition, we also have a number of different support options for integrating Kubernetes, including Rancher, if you're looking for more of a streamlined Kubernetes deployment. So with our bare metal cloud, you're able to deploy instances fast. You can actually have an instance up and running in just less than a couple of minutes. And there's over 40 instance types available in bare metal cloud, with a wide range of OS support for the different types of OSs you might want to use, including Ubuntu, CentOS, Windows, Proxmox, VMware, and several others. And then you're able to bring your own tool set to Bare Metal Cloud. It's fully API driven, so you're able to leverage a number of different plugins we've integrated, built integrations for, including Ansible, Terraform, Pulumi, as well as a couple dozen other plugins that we've released for Bare Metal Cloud. And from a billing perspective, Bare Metal Cloud gives you true bare metal, but you have the ability to consume it with that cloud feel, right? So you can actually scale up and down on demand, and there are options for hourly billing models as you deploy your infrastructure in Bare Metal Cloud. And we're including 1 terabyte of object storage services. So this is S3 compatible object storage with our Bare Metal Cloud services. So that's something that's included complementary with the service. And with that, I'll hand it back to you, Michael.
Thanks, Gerald. So we're going to run another poll, and we'll let that get going, and then we'll see what the results are. Okay, here we go. So, well, it seems like there's a bunch of attendees who have yet to reach out, but several have reached out to phoenixNAP and to MemVerge and to Intel as well. So if you are interested, you can reach out to any of us for further information. And so we look forward to talking to you. Now it's time for Q&A, and we already have some questions. So what I thought I would do is I'll start with the ones that came in first. So Richard Brandenstein asked initially, is PMem the same as NVDIMS? And I thought maybe Sridhar, you might want to answer that one.
No, NVDIM is more like a battery backup DRAM, and this is by nature the Optane 3D crosspoint has a persistent characteristic. So we follow some NVDIM standards, but it's a different technology based on Optane.
Great. And Sridhar, this next one might be for you too. Urushi wants to know if we've tested SAP HANA, in memory on this kind of model, and I'll let either you or MemVerge answer that.
As of now, SAP has certified both memory mode and app direct mode, because at the application level, they have already done the application direct, and we already got certified. So you can use it, but I'll let Charlie comment. But as of now, MemVerge is not targeting SAP HANA type of use cases, which are already app direct enabled.
Yeah, that's right. Yeah, so that primary support comes from SAP HANA themselves for the memory mode and app direct mode. So we're not sort of supporting that right now. Yeah.
Let's see, got other questions coming. Oh, so Rushi asked again, certified ? Was it in the co-innovation lab? I actually don't know the answer to that, but maybe Sridhar, you know more about that. This in relation to her last question, the last question about HANA.
It means it's certified. Hardware is there from OEMs like HP, Dell, Cisco, Lenovo, and all other guys. So it's a TDI certified hardware. So if you have more questions, please reach out to me on LinkedIn or through my email ID. I can put it in the chat.
Yeah, so I guess Richard also asked a question about, are the slides available? I assume they are, but they should be available after the show after this is over. But I'll let maybe one of the organizers comment on that.
Yeah, absolutely. So we will make the slides available. I know there's a number of handouts that will be available as well after the webinar.
Okay, perfect. And I think we're pretty much to the end of our time. Unless there's any more questions, I think that I thank you all for your time, and we'll do the raffle, and so we don't run out of time. Go ahead, Gerald.
All right, perfect. Well, thanks everyone for attending. One moment here and kind of get a drum roll while we get a winner for the raffle. So it looks like Dwight Dietrich is the winner of today's raffle for a $100 Amazon gift card. So congratulations, Dwight. So our marketing team will be in contact to make sure you receive that.
Good job, Dwight.
Perfect. Well, thanks everyone so much for attending today. We hope you found this valuable, and a big thank you to our partners at MemVerge and TGen and Intel for attending and help put this together. Again, thanks so much to the audience for attending and for your engagement in today's webinar. Hopefully you found this to be valuable, and if you have any questions, please reach out. We'll make sure to get those answered for you, or if there's something you want to explore in deeper detail, we'll be happy to coordinate a meeting to do that with you.